Right. So you observed here already six-fold symmetry, right? Remember six-fold symmetry here along these six axes, right? So this is snow crystals, and the bottom one you can see uh, carbon crystals, right? There also you can see some symmetric axes, right? So that means along these axes you can make your crystal into two halves without changing its shape, right? Identical two sections you can produce along these axis directions. And also another important thing is, for example, if you are going to rotate this crystal along this axis, right, along this line, we can take it as an axis, right? Still you are not destroying the shape of the object, right? You see the same object six times, right? If you rotate this one also, you will see the same shape six times. That means six-fold symmetry again, right? So this type of features are very common for crystals. For non-crystalline materials, you can't find this type of symmetry, right? So it's not always six. It may be two, three, four, like that, right? For depending on the crystal. So we are going to learn about the different categories of crystals. We call it crystal classes. There you will observe different symmetries are there, right? Not common symmetries for existing for all the crystals, but the common feature is as some kind of symmetric features are preserved in crystals. So that is one of the prime features related with crystals. So that is an important factor we have to consider under the crystallography, right? If there is anyone who did not input your numbers, registration numbers in the chat box, please do that because we need the attendance marking, right? So here you can see the snowflakes story. You can see different morphologies are there for snowflakes, for snow crystals, but still you can find the features that we have already discussed about the symmetry, right? So other important feature is the composition. Chemical composition is common, right? Irrespective of their shape or anything, the chemistry is same. So this applies to other crystals as well, right? For minerals also this applies. The chemistry is constant for minerals also. We will learn about these things later. And the other one we already discussed, that is the symmetry and the symmetry of the shape, right? So in conclusion, what you can say is there is a specific feature of internal arrangement of the flakes responsible for six-fold symmetry in this case, right? In this case means the snowflake case, right? So this symmetry is a result of an internal arrangement. Actually, the symmetry, what you see here is an external feature, right? Superficial or kind of something related with the shape, but it's a result of an internal arrangement of atoms, right? So this we will consider in detail in the coming slides and coming lectures, right? So it is very important about the internal arrangement, right? So now you have a fair idea about crystals. That means some substances which have a specific shape, specific composition, and specific or orderly arrangement, right? In orderly internal arrangement of atoms or ions, right? So that is what you call crystal. So every mineral, right? So there are more than 3,000 minerals in this planet, right? So these minerals are also crystalline. We call them crystalline because these minerals have some specific shapes. So these specific shapes, specific shaped items, we already termed as crystals. So that means minerals are also crystals, can be defined as crystals, right? So these are natural solids. That means they should be formed by a natural process, not any artificial or chemical process. due to geological processes, right? Due to some geological processes, you can find mineral crystallization. In your other courses, you can learn more details about these geological processes. Okay, right. So, minerals actually are the largest source of naturally formed crystalline solids. So, naturally formed crystalline solids, if you consider, minerals compose a large group, right? Minerals are a large group of crystalline solids. So you can see here, these are quartz crystals, right? Quartz, Tiruvana. You know quartz already very well, right? Actually, the if they are perfectly crystallized, if the quartz is naturally crystallized perfectly in perfect manner, definitely you will see this type of phases, right? These are the crystal phases available in quartz crystals, right? So you can observe them if this particular mineral quartz was allowed to grow very slowly, right? If it was allowed to grow very slowly, you will see development of these crystal phases. Otherwise, these crystals will be developed, but external shape would not be preserved as beautiful as here, right? So you can see here very nicely shaped crystals, natural crystals of quartz here, right? But if you go to a place where you see big quartz quarry, right? Quartz bearing quarry, which we call quartzite rock, right? Tiruvana gal kela, right? So if you go there and inspect the material, you will not see these beautiful shapes, but rarely you might find very nicely crystalline materials of quartz, but you don't see them mostly, right? It's because the external other factors which was prevailing during the crystallization process. But if you go to some other areas like Buttala or Mahatale even, some places we call a specific rock pegmatite, right? So these pegmatite rocks are magmatic rocks. They are produced from magmas, but they have been crystallized in a very slow rate, right? At a very slow rate, so that you will see there very big crystals, right? Very nicely crystalline quartz, not only quartz, corundum, like there are several mineral types. We will learn about these minerals later on. So many other types of minerals you can find in very nice shapes, very beautiful shapes. So even here you have some other mineral, which I think a hornblende, right? We call another mineral a hornblende. There also you can see some phases, right? See here, some beautiful phases are there, but color is different, other properties are different. Luster, or the way you observe them, like the glossy feature, right? That is what you call luster, right? That is also different, right? So all these things are dependent on each and every crystal. So that means different crystals have different shapes and different physical properties, right? So these things we will learn slowly. So you will understand the importance of these physical properties. Okay, right. So crystalline materials are having an orderly arrangement of internal atoms, right? So that is an important factor, so that they can define specific shapes and also specific symmetries, right? That is the important point that we have to keep in mind. And as common features of minerals, that means crystals which compose minerals, they have natural facets, right? Natural facets mean the phases, right? Crystal phases, right? These are called facets, right? You can see these are facets, right? Different types of facets, and they kind of flat, and not only on the superficial level, but also in atomic level also they are flat, right? So we can observe them in atomic level using an electron microscope. Normal microscopes you can observe like this, right? This type of things you can observe and get a picture like this. But uh, in atomic scale, if you are going to observe them, you need to use a electron microscope, right? In our department, we have an electron microscope at the first floor, at the ground floor of the white color building. There we can observe this type of atomic arrangement of crystals, right? So these are electron probe or electron microscope images, right? SCM images. We call them secondary electron images. Okay, right. So crystal morphology observation is important in crystallography. It can be done through an optical microscope, normal microscope, right? But it's different microscope, right? In the second year, you will learn about microscopic features in detail. We call it a polarizing microscope, right? What we have is a polarizing microscope with normal biological microscope that you use in botany or biology, in zoology, or blood specimen observation. We can't use them for geological material observations, especially minerals, because we need some other technique that is called polarization effect, which that type of microscopes we need, right? So anyway, external shapes of minerals are very common, but the shapes themselves are not the same shapes. They are different shapes, but the thing is they have a type of special type of a shape, right? So this is a important feature. And another image you can see at atomic level by electron microscopy, right? There you see natural phases, right? You see the natural phases at very small scale. So I don't know whether you can see clearly here the scale. Let me see. Yeah, no, not the scale is given, but the magnification is given here. Right? 170 times magnified than the normal size, right? So these are micrometer or nanometer scale, right? This is micrometer or nanometer scale, but still you can see the same shape is observed, right? Atomic level also you can see the same feature like in the what you see in this macroscopic scale, right? So these are the common features that you can observe in terms of crystals, right? Do you have any questions regarding this content so far? And do you have another lecture at 11 o'clock? Any other lecture? Is there any other lecture at 11 o'clock? Because I can cover the time that we missed. If you don't have lecture, please let me know quickly. If somebody is having a lecture, please let me know at 11 o'clock. Online lecture. Right. So the birth of crystallography was a long time ago, right? It was around 1600. This was around 1600. Uh, First, the Nicholas Steno and another scientist, Rom D. Leslie, they invented some consistency of the interfacial angles. That means they observed some kind of a consistency of interfacial angles. Then, for example, here you can see one face and another one here, right? So this angle between these two faces we call interfacial angle, right? It's a constant for this particular mineral, right? This was not known at the very beginning. Okay, you don't have lectures, right? So I will continue then for a while. This interfacial angle was constant for different minerals, right? So this was invented by these people, right? So that was given as a law, which is called law of constancy, right? Law of constancy for a given species. Remember, right? Different species have different angles because they have different shapes. But for a given species, the angle is constant, right? Interfacial angle. So that means they define a specific shape. If you consider quartz should have a specific shape. If you don't have interfacial angle consistency, you will never observe them in a common shape, right? But for diamond, it's different, right? But every diamond will have same shape, right? Crystalline diamonds. So that law was invented in 1600. This is called the law of constancy of interfacial angles, right? So this is related with the origin of the crystal, right? So it's a very characteristic feature for that particular crystal, right? And then there was another law invented about 100 years later that was called the law of rotational indices. Actually, there are some indices that we are going to define little while later. These indices means actually when if for example this quartz crystal right here, if you can put if you can assign some access for this quartz crystal, for example, if you want to assign one direction like this, elongated direction like this, right, and another direction like this, and another direction in the 3D three-dimensional phase, so XYZ directions, right? So we can assign directions like this for each and every crystal, right? These directions in crystallography we call ABC directions, ABC, right? ABC directions, and you can see some specific length for, a kind of ratios, specific ratios of length that intersect these crystals, right? For example, here one face intersects at here, right? The length is different here, say X here, and this length, the other axis, maybe you can call it X, right? Its length is different than the previous length of that crystal. Similarly, for the Z axis or C axis, C or Z, anything is okay, right? In crystallography, these are the access notations, right? So this is what is called rotational axis. So they invented that natural phases of crystals cut the lengths proportional to the three integer numbers, right? Some integer numbers, that means for example you can assign 1 as along one direction. For example, if you assign 1 here, this may be 3, so it's proportional, right? Here you can define it as 3 sections, here just 1, like that, right? Maybe the other direction 2, right? So likewise there is some kind of a relationship, right? This relationship was invented in 1700. It's a kind of a mathematical relationship, more or less mathematical approach, right? So crystal phases, to describe crystal phases, they have used some axes called ABC. We call it them crystallographic axes, and there they found that the intersection points of these axes of each phase is proportional to some integers, right? We will see the exact idea about that later on, but just keep in mind that this is called the law of rational indices, right? Law of rational indices, because ratio this one. The ratio has some relationship, right? Depending on the crystal, right? You will study this under a different name later on, which we call Miller indices, a kind of an indices, kind of an index actually. We will see that later on, right? So, for example, here, okay, let's take this example, the bottom one first. The natural crystal is here, right? Natural crystal is here, so you can see the faces right here and here and here, right? So you have three directions actually. So these three directions can be represented by a long axis and intermediate axis and a short axis, right? So you have one long axis, one short axis, one intermediate axis and one short axis, right? So the places where this crystal intersects along this uh, axis is rational, right? You can make it into proportions, right? Maybe in one direction it's 2 times, in other direction 3 times, in another direction maybe 1 time, like that, right? So like this, you may be able to draw this crystal along this, orient this crystal along this axis. So this is what they were talking about, right? The second law of rational indices, right? So this is a model, the upper one, this one is a model of another crystal. Its shape is called rhomboidodecahedron, right? Rhomboidodecahedron, right? Here pentagondodecahedron, the shape, right? Because the face here is represented by a pentagon. Here it's a rhombus, right? So this is very common for garnet, the mineral garnet. You may have heard of garnet, right? Garnet has, if it was crystallized perfectly, you will see this shape, right? Each and every natural mineral has a specific shape. So you can see, you can even maybe difficult to imagine how these beautiful shapes are produced, right? So these are natural processes. So anyway, in this case, garnet actually, even though you did not learn it yet in detail, you can see here, if you put 3 axes there, right? XYZ axis like this, right? Or ABC axis, right? For crystallographic axis, A, B, and C, right? And you will definitely see this crystal cross cuts these axes in equal lengths, here, here, and here, unlike the previous example, right? So there one axis is longer, the other axis is intermediate, and the next one is shortest. But here you see A equals B equals C, right? All are same, right? So that is one of the features of this particular crystal. So in garnet, you can see all the axes are equal, right? A, B, C axes are equal. But for another crystal, it's different. For quartz, for example, you saw that here quartz is also having an elongated axis, right? And some short axis and some intermediate axis also, right? It all depends on the crystal shape. But in the case of garnet here, it's equal, right? So actually garnet we call it's a cubic system, right? We will learn about these systems later. So this is a cubic system. That means for all the directions, the axis lengths are equal, right? So anyway, this is a feature observed by this scientist. Actually, he's a mathematician. It's called the law of rational indices, right? It was like 1700, just after the law of constancy, right? Interfacial angle law, right? So those are some important aspects related with crystals. And another thing is about physical properties of these crystals, right? So when we take when we consider about physical properties, you should be noted that the physical properties are changing depending on the crystal axis also, right? So that means if you, some physical properties, right? Not all, some physical properties can change along this axis direction. For example, in x direction, physical properties are different in some cases. For example, conductivity. Electrical conductivity is different along the direction, right? So it's all because of the internal atomic arrangement, right? The way the electrons are moved from one direction to another, that all depends on the crystal internal arrangement, right? So conductivity changes, so we call it anisotropy. Anisotropy means inequality, like inequality, like, right? It's not equal in all directions. If something is equal in all directions, for example, here you can call this garnet a kind of isotropic mineral, because all the directions, they have similar properties, right? Even electrical conductivity, same for this particular case, right? So then it's isotropic. We call it isotropic. All directions have same properties. But in if you have different properties in different directions, then you call it anisotropic, right? Anisotropic or anisotropy, right? The feature you can call. So all these things depend on the growth velocity and the formation of facets in each material. Okay, so this is regarding the physical properties. And for example, you have another mineral that is called tourmaline, right? We call tourmaline it's a gem mineral. It's a gem mineral. In Sinhala you call it tourmaline, right? So tourmaline has a specific feature, another specific feature with regard to electricity, right? That's what you call the pyroelectric effect. Pyroelectric effect, right? Pyroelectric effect means the separation of electric charges in a crystal as a result of temperature variation, right? So in one side you have one temperature and the other side another temperature. So because of this temperature gradient or temperature dependence, some electric flow, some electric current flow can be observed. This is called the pyroelectric effect. In some minerals you have this pyroelectric effect, right? So this is anisotropic. This is anisotropic. That means it's not equal in all directions, right? In this direction it's one way, and the other direction it is another way, right? So that's because the electric charges are developed only along in certain directions, right? Certain phases of crystal has these different effects of these electrical charges, the movement of electrical charges. So therefore you observe uh, heterogeneous distribution of electric current as a result of this temperature dependence, right? So that is called pyroelectric effect, which is common for some crystals. And further studies on these electric conductivity in minerals was done by Pierre Curie, the husband of Marie Curie, right? French scientist. And what he discovered was piezoelectricity, another important feature of electricity, right? So there, the main reason for that is electric charges are developed by external pressure. So when the pressure is applied on the crystal, some electric charges are developed, right? So this is called piezoelectricity, right? So in some crystals like quartz, even you can find this type of piezoelectric feature. So that's why some quartz crystals are used in watches. Okay, so anyway, these are anisotropic, right? Their variation is anisotropic, and this anisotropy is basically because of the different internal arrangement of atoms, right? But the thing is, periodic structure is observed in mineral in crystals. So that means same structure is repeating, right? For example, here this is an example, right? So you can see the same structure is repeating, right? So this same structure is repeating throughout the material, right? So that is a feature of a crystal, right? It's a kind of an orderly arrangement, right? We told that the orderly arrangement is a feature of a crystal, one of the features of the crystal, right? Along this direction, you have this type of orderly arrangement. But along the other side, you don't see that feature, right? You see, this part is different and this part is different, right? So that means the periodic arrangement is not isotropically distributed, right? It's not distributed isotropically. So does the electric or other uh, physical features also, right? So it's not common for all minerals. Some minerals have same type of feature in all directions, like garnet is you just observe, right? But for some minerals it is only along one direction. So that's the reason for this anisotropy. Okay, so this is what Pierre Curie was trying to emphasize there, the anisotropy of crystals due to its variation of the periodic structure. Okay, right. So those are two important factors. And another example, the repeating units you can see here. Sorry, you just observe these the two objects which are which is there in the red box. You have one bird-like feature here and another bird-like feature here, right? So these two are repeating, right? Here also you can find, right? Everywhere you can find the same feature is repeating, right? This is repeating in all directions. I mean, main two directions, right? This way also you can see, and also this way also you can see the same feature, the periodic structure repeating. So here you can say that this crystal is isotropic, right? It's same. But the other patterns, for example, here you can see some kind of sorry, it's not clear. Which color is better? Yellow. You see this structure, this shape, right? Something circular, right? This is repeating here also, right? And maybe here also you have one, right? Here also isotropic. This way also repeating, this way also repeating, right? And in this case, here you have one structure which is repeating in this direction and this direction, right? So in along some particular directions, you can see these features are the periodically distributed features are there, right? So these are common for crystals. Each crystal has its own periodic arrangement of atoms, right? So these factors determine whether isotropic or anisotropic property of a given crystal. Okay, so these features, these physical properties are changing because of those type of internal arrangements of atoms, right? These are atomic arrangements. So actually it's a kind of a pattern, right? So that's why we consider different patterns in crystals in addition to symmetry, right? Some atomic patterns are observed in crystals. So that is what you call the orderly arrangement, right? Systematic internal arrangement of atoms. So uh, that's a feature of a crystal, right? Do you have any questions on this content? Okay, right. Uh, Crystallography has direct relationship with physics, right? Mainly solid state physics, right? So when the solid state physics principles came into more popular in the world was due to crystallography. Actually, the more details of crystallography was known means it's the initiation of the solid state physics concepts, right? So in 1914, Max von Laue uh, won the Nobel Prize in Physics for uh, studies of X-rays in crystals, right? So he observed some specific characteristic feature of X-rays when X-rays are bombarded into a crystal. So he observed some systematic behavior or kind of a diffraction, right? You know, diffraction, not refraction or reflection. It's diffraction, right? When a ray travels through a material, it can change its path, right? Not just refraction. It's kind of a scattering like feature, right? That is called diffraction. Right? So X-rays are diffracted in crystals systematically, by crystals systematically. So that was invented by him in 1912. So that is where the solid state physics also started, right? So from an X-ray source, if you have some X-rays produced and bombarded there on a crystal, depending on the crystal shape, right? Because you know crystals are orderly arranged, right? So internal atomic arrangement is fixed there. So these X-rays can diffract. That means they can change their angle in an orderly manner, right? Symmetric manner, right? So you will see similar distribution of these X-rays after they are getting diffracted, right? On a film, photo film, they can be recorded, right? So this is how you observe on a film, right? They are hitting the places where the X-rays hit, right? You can see some kind of a systematic feature, very systematic feature. That all depends on the crystal shape, right? So that is pattern, the first pattern observed by them, because crystal X-rays can diffract in a systematic way, right? Because the period of crystal lattice is important. The periodic arrangement of atoms inside a lattice. Lattice, you know, the crystal structure. Due to that, these diffraction of X-rays are giving in some orders of wavelengths in terms of wavelengths, right? So there is a systematic relationship, right? So this is a very important finding about X-ray diffraction, right? So here you see the diffraction patterns, right? This is quartz crystals. Once quartz crystals are subjected to X-ray diffraction, you can find this type of distribution. So these spots, the intense spots are called Bragg peaks, right? This was invented by another person, right? Bragg. I will show them, introduce you him also, right? So this is from quartz, right? So you see, they have some consistency about the shape also, right? So this is X-ray diffraction pattern actually. So using this pattern, people can recognize what kind of crystal it is also, right? If you can't determine it physically, we can use X-ray diffraction to find out, right? So this is kind of an proof of the periodic structure of crystals, because we just thought there should be a periodic structure uh, I mean, in terms of atoms of a crystal, that should give you a kind of a systematic pattern, right? That was proved, that concept was proved by his experiments, right? But remember, these small lengths in between are in very small distances, right? Those are in angstroms. So angstroms means 10 to the power minus 10 meters, right? So you can imagine how small that unit is, right? So anyway, uh, this was mainly these experiments were mainly done by two Braggs, W.H. Bragg and W.H. Bragg. Actually, they are uh, father and son, those two scientists, right? So they invented these Bragg's patterns and peaks in a crystal, right? So that's why nowadays we use X-ray diffraction for identifying structures in materials, right? Especially to characterize crystal structures, right? These are the two scientists who invented that pattern, right? So by that observation, right, by these observations, they could uh, conceptualize in 3D about the crystal shapes, right? So this is the real crystal structure first invented by them, and they also won the Nobel Prize and shared both of them. Uh, for example, sodium chloride, KCl, and lithium fluoride, they first established the atomic structure. So it's a kind of cubic structure, right? It's a cubic structure. This is cube-like feature, right? Garnet is also same, right? Cube-like, but you saw the difference in garnet. It has a, very different rhombohedral shaped peaks also. But actually, being these axes are equal, you can term this as a cube also, right? So this is inside a cube. You can put this garnet grain in the inside the cube, which has length equal lengths of these ones, right? So that's why it's a cubic shape we call, right? Even this one cubic. Some derivation of this shape is a derivation of a cube, but it is systematic derivation, right? Pentagonal, or here is rhombohedral. Right. So these shapes of crystals were uh, then could be determined by X-ray diffraction patterns after their experiment. Okay. So this is the first construction of the crystal structures. Right. So likewise, people came up with many other different shapes of crystals also, right? So diamond, it's called octahedron type, right? Here, it's like octahedron shape, right? You know the octahedron shape, right? Top and bottom like this, and it's three-dimensional. So this is the octahedron shape of diamond, and quartz having hexagonal but prismatic. It's elongated. We call it prismatic, right? Different shapes. So these shapes can be derived, I mean, reshaped, but still the same principles, axis, should be kept constant. Like in the cubic case, in the garnet situation example, right? So these are very important observations that was derived after X-ray diffraction patterns. So what we learned so far is the internal structure of these crystals. So they are, I mean, the materials or the crystals and their atomic packing we talked about, right? So for a crystal, it should be orderly, right? It should be orderly, or in other words, we call it periodic. Actually, it's 3D, right? In 3D arrays, maybe, because it's not one single atom. It's a group of atoms, right? Here you see it's a group of atoms. There you can observe the periodic pattern. This is one unit, right? One group, right? One group. So they are systematically distributed, right? They are systematically distributed. That is what you call the periodic arrangement. But in some materials, you don't see this systematic arrangement. For example, here you have one shape, and here you have another shape, right? And here some other shape. So that is not systematic. So wherever the systematic internal arrangement is there, we call them crystalline materials. If not, we call them non-crystalline materials. Okay. So all the minerals, all the crystals are crystalline solids, right? So they have orderly arrangement, but there are other materials which are non-crystalline. Okay. So now you know the materials basically can be divided into two groups: crystalline materials and non-crystalline materials. Okay, so minerals are crystalline materials. Essentially, minerals are crystalline materials. Not only minerals, metals, some ceramics, and polymers. Right? Not all ceramics and polymers, but metals are okay. Right? They are crystalline, and you have to add minerals also here. All minerals are crystalline, right? So they have orderly internal arrangement. And non-crystalline materials, where you don't see any orderly arrangement of internal structure, uh, uh, there you can find some glass, for example, the produced glass, like the window glass, for example. It's also silica, SiO2, made of made of silica, uh, which you can uh, classify as amorphous material or non-crystalline material. Amorphous is another term for non-crystalline materials, right? So basically, we have crystalline materials and non-crystalline materials. That means crystals and amorphous material, crystalline and amorphous materials. Right. So this is what we have to keep in mind about crystals, right? In crystals, we have orderly arrangement, and amorphous materials, we don't have any orderly arrangement, right? It's random. There is no systematic uh, arrangements. There are some materials called polycrystalline also. These polycrystalline materials also have some orderly arrangement, but there are some deviations, but still it's kind of like clusters. Within the cluster, it's very orderly arranged, right? So that's why it's called polycrystalline. Now, different clusters of crystalline materials, right? So these three materials are available, whether it is single crystal or polycrystal, right? So the amorphous ones, they don't have proper arrangement of the internal structure. Glass is a very good example. And quartz, naturally occurring quartz is there as a crystalline material, but fused silica, that means if you dissolve silica, natural silica at high temperature, you make it a magma, right? You make it a liquid and then crystallize. So there you don't find any crystalline silica. You will find silica, but it is amorphous. SiO2 is there, the chemical composition is there, but it's not crystalline, right? So these type of two different two different materials are available, right? Okay, so Today we talked about the basic features of crystals and how the crystalline materials, crystalline solids are different from amorphous materials. Amorphous means non-crystalline materials, right? So shape is one of the important factor. For crystalline solids or crystalline materials, you must have uh, naturally formed phases, right? Faceted structure is there. That means some shape is there, some definite shape is there. But for amorphous ones, there are no specific shapes for that, right? And some properties can be anisotropic or isotropic, but actually some exceptions are there. There are some minerals also, some crystals also having isotropic properties, right? So it's better to say both isotropic and anisotropic, but majorly anisotropic. Both is there, but majorly anisotropic crystalline materials. Amorphous materials are isotropic because you see everywhere the same atom is there. So orderly arrangement is not there, although we can't define crystalline axis anyway, but chemically they are homogeneous, right, along all the directions. So therefore, it's called isotropic behavior, right? Then atomic structure, it's periodic, right? Periodic uh, ordered arrangement is there for crystals, but for amorphous materials, there is no periodicity, right? There is no periodicity, but very short order periodicity can be observed. For example, if you take this part and there is similar part maybe here, right? These two more or less orderly, but very short distance only. I mean, if the material is large volume, you don't see this periodic orderly arrangement consistently throughout the material. For example, here also you don't see the same shape. It's different. So that means it's not orderly arrangement. And X-ray diffraction, in terms of X-ray diffraction, the crystalline solids will give you well separated diffraction picture, right, with distinct spots, right? You saw that before. You see, these are the distinct spots for a given crystal, right? For quartz, this is like that. But if you put the garnet, it won't give you the same shapes, but it will give you different spots. I mean, some different shape. Okay, for a given material, it is specific. But the amorphous materials, you don't see clearly separated as clearly separated feature, right, by X-ray diffraction, right? So these are the very basic introduction to the beginning of crystallography, right? So in the upcoming classes, we'll be looking at different features, especially related with symmetry, symmetric features or patterns they exhibit, right? So I suggest you go through this content again before joining the next class. So we will be having another class probably next week, but tomorrow I think you are going to have another lecture that will be done by Dr. Nadisha Kordegadar on fossils, right, paleontology. So both subjects will be going parallelly so that you can cover the content more quickly. That's right, right? So most probably Monday morning, 8 o'clock lecture will also be taken by me next week, right? So do you have any questions regarding this content? Okay, if not, we can leave. You can leave here. So we'll meet next week.